Hello, am I audible to you?
Yes, you are audible.
Thank you. So, my screen is also visible, right? I hope my screen is also visible.
Yeah, yeah, it's visible.
So, welcome to the today's session on electrical machines one. So, basically, this deals with the week 11 portions of the lecture, which was covered by Professor Tapas Kumar Bhattacharya of Department of Electrical Engineering, IIT Kharagpur, and myself, Shiva Prabhakar, and I am a PhD scholar at IIT Bombay. And my area of research is in uh, electric vehicles. Uh, so this is basically a doubt clearance session and as well as a problem solving session where I will be solving some of the problems as well as clearing the doubts which are related to the topics which are covered in the particular week. So a quick recap of the sessions with like the topics which are covered in the particular week. The session mainly included discussions on series motor. As you know, the series motor is like the field winding is connected in series with the armature terminal. So we call it a series motor. The previous week, the discussion was mainly regarding a shunt motor, where the shunt uh, field winding was connected in parallel to the armature. So that was the difference. And there will be within the armature, we can represent it as a resistance and a back EMF EB. And this is the series field winding. And this is the shunt field winding. And this is the main difference between a series motor and a shunt motor. And here we will be applying the voltage V, the terminal voltage, and here similarly we will be applying the same terminal voltage. And here the difference is the field current as well as the armature current is same. In here, separate current flows through the field winding as well as the armature winding, which we call it as IA and IF. Here we call the whole current as I, which is the supply current itself. Here we call the supply current IL, and the current is divided into two parts. And the basic equations of series motor are also discussed. So for both the motors, the basic equations are that for any DC motor is that of back EMF as well as the electromagnetic torque. The back EMF EB is given by K some constant into flux into the speed, and the torque is given by some other constant Kt into flux into the armature current Ia. So if in any case it is mentioned that the flux is not saturating, then we can assume that the flux is proportional to the field current IF. So in that case, we can denote this particular expression as another constant Kt into IF into N, and similarly the torque as Kt dash into IF into IE. So uh, in case of a series motor, since field current is same as that of the armature current, which I am representing it as capital I, so EB will be K dash into I into N, and similarly torque will be Kt dash into I square. So these are the two equations, basic equations for a series motor, and from this the speed versus current characteristics was also discussed, because if you can see back EMF by normal voltage like applying KVL, we have V minus I into RA, and from this you will get a relationship between speed and the current, which is seems to be inversely proportional. So a characteristics of like this speed versus current characteristics was of this form. So if you try to operate the machine at no load condition, that is at current equal to 0, the speed will be dangerously high, as you can see from the characteristic. This is a basic explanation of that thing, and the detailed explanation was made by in the particular lecture. You can go back and refer to that. From the graph, you can directly get into this conclusion. So it is mentioned that the DC motor, series motor should not be operated at no load condition. There should be some minimum load which should be applied. And similarly, there was some discussion regarding the fact that the shunt terminal of a shunt machine should not be open circuited. You should always ensure that the connections are there proper. Otherwise, what happens is the field current will be zero, so the flux will not be generated, so the speed can again go dangerously high. So, and similarly, the speed control of series motor was also discussed. For this particular case, the speed control below the rated speed can be controlled by controlling the voltage below its rated voltage. That is the basic condition. And the torque versus current characteristics was also discussed. As you can see, the torque is proportional to I square. So the actual torque versus current characteristics will be a parabolic shape because it is proportional to square. But since we incorporate saturation, after some particular point, what happens is that we already know that it is kT into pi into I. After some point, this flux will become a constant. So at after that particular point, that is after saturation, so it will be torque will be proportional to only current. So it will be a linear after saturation. So these were the things which were discussed, and in order to control the speed below the rated voltage, rated speed, we are controlling the voltage. That is, since we are operating it at rated voltage, we can bring down the rated voltage and apply a lesser voltage to control the speed. Because as you can see, uh, EB is K phi into N. So V minus IRA, which is the KVL equation, is K phi into N. So you can write like V by K phi minus I by K phi into RA is N. So if you are equating it to current as well, so we can get that K dash into I minus I by K dash into I. So this I and I will cancel, and it is RA. And as you can know, RA is a very small quantity. So V by K dash into I is approximately equal to the speed. So we can control the voltage to control the current. Another method is to control the current. So current, if you can see here, the field winding is in series with the armature. So whatever changes you make in the field resistance, the same will get reflected into the armature terminal as well. So in that case, different discussions were made in order to control the speed above the rated speed. So below the rated speeds, we can simply reduce the voltage, and above the rated speed, one method is to change the value of the field resistance without affecting the normal current. So a method of field diverter resistance, a tap changer, as well as different combination of field windings were discussed. So if you can see, in case of a four-pole machine, there will be like windings will be there. So these are the field windings in case of a four-pole machine. So you can represent it as four separate windings. Either we can connect them in series, you will get a particular combination of RSC, that is the field resistance, or you can connect all of them in parallel like this. So this will form another combination of field circuit. So here the current will be I by 4 if the total current is I, and here the current through all the field windings will be I itself. So by different combinations of the field windings, you can have different resistances in the that is different value of RSC, and thus the current through the field winding will be different. So the flux, which is proportional to I by in this case, it will be proportional to I by 4 as against I in this case. So there we can manipulate the value of flux by rearranging the field resistance combinations. That is another method. And another method is regarding adding a resistance which is known as the diverter resistance, which I am calling RDI, in series in parallel with the field winding, so that we can control the value of field current IF. So if this is the current, so the field current IF will be by applying resistance division R by RSC plus R diversion, that diverter resistance into the net current. So this will be the value of field current. As against, if this diverter resistance was not there, IF is nothing but I without diverter. So these were the some methods which were discussed regarding the field resistance control. So, and there were discussion regarding series and parallel connection of motor by connecting them two motors in series as well as two motors in parallel. So what will be the voltages appearing across the net, across the terminals of the motor and all those cases in there. We will be applying the same supply voltage, but there will be two series motors. So across each motor terminals, we will get V by 2, V by 2. So these were some discussions. And what were the issue with interchanging the supply terminals was also discussed, whether the motor behaves in the same manner or not. And universal series motor is also called a universal motor because it can operate with both AC as well as DC. So these were the few things which are discussed. And the testing was also introduced regarding the DC motor, and Swinburne's test was also discussed. The Swinburne's test is basically we will be operating the machine at the motor at no load, such that since there is no load, whatever effort the motor makes, which will be wasted as rotational losses. So whatever power output is there, that will be reflected as the rotational losses. So that is how Swinburne's test is conducted. Since it is conducted at no load, it does not dissipate any power outside. Only a rotational loss will be available. And in case of DC brake test, what we do is we will be directly loading the motor. And in that case, what happens is that the motor will get unnecessarily loaded just for testing purpose, and whatever power in which the motor is running, as we load it more and more current will be drawn, and there will be more lot of losses occurring in the motor, and that will be dissipated within the motor, and it will be wasted. So it is not good to conduct this test, and this Hopkinson test was introduced, and it is not covered as such, so it will be covered in the next week. So is there any doubt in the particular sections, any of the topics? I am just giving a quick recap so that you can reflect and ask your doubts. If there is no doubts, I will proceed with the problems.
Okay, sir, no problem. In this,
Okay, then I will proceed with the problem. So, no doubts, right? So I will proceed with the problem. So the first question I am discussing. So as I have discussed, the problems will be regarding DC series motor. So let's go to the first problem. So in the first problem, let me read the question first. A 240 volt 8 pole DC series motor had 8 field coils connected in series. So there are 8 field coils for this particular DC motor, and they are connected in series, it was mentioned. It was given that the machine was drawing 20 ampere current and driving a fan load at 900 rpm. So initially, with this particular combination of field winding, it was drawing a 20 ampere current and driving a fan load of 900 at 900 rpm. So it was driving a particular load so that the motor is rotating at 900 rpm. And it is mentioned that the load torque is proportional to the square of the speed. So in this particular problem, the load torque is not a constant, and it is actually proportional to the square of the field speed. So as the speed varies, the load will also vary in this particular case. So as against the most of the discussions made in class where we take the load torque to be a constant, here load torque is not a constant, and it varies with variation in the speed as well. So that is one condition given. and it is mentioned that the magnetizing curve is linear. So we can consider that the flux is proportional to IF and all the losses are neglected. Now the field coils are reconnected in two parallel groups of four in series. So now they are changed the field configuration. As I have discussed, it is one of the method to control the speed. So one of the have different combination of the field resistances, and they are asking to estimate the new speed and the new motor current. So we need to find the new speed and new motor current. So let me, after reading the question, I will identify which all are the parameters given to you. So it is given that it is a 240 volt supply. So I can write that P is 240 volt and it will be a constant throughout because it is the supply terminal and it is not mentioned that the supply voltage is varying. So V is 240, so I am considering it. And it is a 8-pole series motor. So number of poles is given to you as 8 and it has 8 field coils. As I have discussed earlier, for a 4-pole machine, if it was a 4-pole machine, then there would have been like 4 sets of series winding, like field windings, right? So here, since it is an 8-pole, there will be similarly like this, 8 poles will be there. And similarly, 8 series windings will be there. So this figure looks clumsy. So this is the idea. So there are 8 sets of series windings. So like this, there are 8 sets. And initially it was mentioned that these were connected in series. So these were the initial configuration. So this everything was connected in series and it was given that, so this one I will represent it as a big one like this. So this is equivalent to this. So it is a DC series motor. So whenever a motor is given as DC series motor, I will first of all draw the equivalent diagram. So I am representing it as a single resistance for the series combination. So I am considering it as R1, combination as R1, and this is the motor general structure. So there will be a motor and this is the field winding. Now there is an armature resistance and there is a back EMF and it is connected to a supply. So this is the first condition and it is given that in this particular combination of field resistances that 8 different windings are connected in series to form a single resistance. The current drawn is 20 ampere. So if you can see here, all the field windings will carry the same current. So I will be the current, that is 20 ampere will be the current flowing through all the field terminals. And it is driving a fan load such that fan load and the motor will therefore operate at N1 equal to 900 RPM. So it is also given to you. Now the load torque is proportional to, so I am representing load torque as TL and it is proportional to speed. So that is the condition given to us. And the magnetizing curve is linear. So this is an important point. So let me mark which all are important. 20 ampere current is given to you and the fan load at 900 RPM. So N1 I am taking it as 900 RPM and the load torque is proportional to square of the speed. So TL is proportional to n square. So I have missed that. So it is proportional to n square. So that is also given to you. And the magnetizing curve is linear. So flux we can take it to be proportional to the field current. So flux is proportional to IF. So this can be obtained from this particular statement and it is given that all losses are neglected. And now they are saying that this particular combination is set to new combination such that it forms two parallel groups. Two parallel groups. So there are two groups and in each groups there are four windings in series. So this is the new field circuit. So this current I am calling as I1. So if you can see here for the first case, this is the second case. I'm not representing it here. Here I'm representing a single resistance for the series combination, and here now it is like this, and this is the case number 2. And similarly, there is RA. RA will be a constant, and EB2, let me represent, this is EB1, and this is a constant RA. The supply voltage is same, so supply voltage I am marking it as V only, and EB2, EB1, so I am distinguishing it, and the current I am marking it as I2. And now if you see, the current here will be also I2, but it will get split into two parts. That is, I2 by 2 will be the current through two field terminals. So if you see that it is a parallel combination of two parts, so the current will get split into two parts. So the new flux will be proportional to I2 by 2. So this is the important thing. So new flux will be proportional to I2 by 2. So this is the things we will get from first part, that is it is proportional to I1, and in the second part the new flux will be proportional to I2 by 2. So is there any doubt in understanding the question?
No, sir. Proceed further.
Okay. So from the first case, from case 1, you can write EB, is K phi into N. So we can write EB1 to be K into some K dash into I1 into N1, because field current is same as I1. So flux here is proportional to I1. So this is our first equation. And second equation, let me let the torque which is given to you, and it is given that torque TL is, you know, is KT into uh, flux into IA. So here IA and I1 are same, so you can write it as KT dash into I1 square. So here. So these two we can write for case 1, and similarly for case 2 also same equations hold. So we can write AB2 equal to K dash into I2 by 2 into N2, because now flux is proportional to I2 by 2, and TE TE2 equal to KT dash. The constant remains the same. That's why I'm representing it as the same thing. I2 by 2 into I2. So this will form my equation number 3. Same condition I am applying. The flux phi 1, and this is phi 1. So phi 1 was proportional to I1, but phi 2 is proportional to I2. So I2 by 2. So that is the only change. So far any doubt? Any doubt in
No,
this
sir.
particular expression? Okay. So let us now go back to the condition, what they are asking for. They are asking for the new speed. So we need to find the value of N2 and new motor current I2. So N2 equal to question mark and I2 equal to question mark. So we have identified what we have to find out, and these are the things which we need to find out. So uh, so it is also given that the load torque is proportional to N1. So at steady state we have TL equal to TE. So we can write TL1 by TL2, that is the load torque in two different conditions, is nothing but N1 by N2 the whole square equal to, that is nothing but TE1 by TE2 So that is from this particular equation we can write I1 square by I2 by 2 into I2.
Hello, sir.
Yes.
Here, as per question given, TL directly proportional to n square, but you are written here uh, TL directly proportional to only n.
Okay. And sorry. Thanks for that. Here I have written correct. Okay.
Okay.
So n1 by n2 the whole square. So these things we can write. So here it is nothing but 2I1 square by I2 square equal to n1 by n2 the whole square. So this is my equation number 5. So these all things I have identified. So let me first substitute, and from equation 1 you have a relationship between EB, I1 and N1, and equation 3 you have a relationship between EB2, I2 and N2. So EB1 by EB2 will be nothing but I1 N1 by I2 by 2 by N2. So EB1 by EB2 equal to 2I1 N1 by I2 into N2. So this is our equation number 6. So is there any doubt till now? I have just substituted these things as a fractional form. So there is two important equations available to you, and we have that is a relationship which is connecting I1, N1, I1, I2, and N1 and N2, and another equation which is connecting the back EMFs with the two currents and voltages. Now two currents and speeds. Now let me substitute the values of I1 N1 which is given to you. So I1 is 20 ampere and I2 and N1 is 900 RPM, and let me substitute that. So I1 is 20 ampere and N1 is 900 RPM. It is given to you. And in the question, if you have noticed, there is no mentioning about the value of the field resistance as well as the armature resistance. So we can neglect this particular values, that is our this particular combinations. So we can approximate that EB is approximately equal to B, because
Supply voltage.
we have been not given the value of RA, the field resistance or anything. So we can see that we can approximate it to be a same value. So EB1 by EB2 now will become 1, assuming RA negligible. So this is the important assumption we are making. So EB1 by EB2 will become 1. Now the problem is quite simple. So we have three basic equations, 1, 2, 3, and we have two unknowns. So we can simply calculate it. So from this you can say that 2 into I1 N1 by I2 N2 will be equal to 1. So you have the value of I2 into N2 will be nothing but 2 into I1 N1, and if you substitute the values it will be 2 into 20 into 900, and it comes out to be 36,000. So I2 N2 will be 36,000. So this is equation number 8. So is there any doubt till now? Is there any doubt in your paper?
No
Is there
doubt,
any
sir.
doubt? Yes. So we got a relationship between I2 and 2 which is equal to 36,000. And from this you can write that is 2 into I1 by I2 the whole square equal to N1 by N2 whole square. Now I simply can take the square root of this, that is root 2 into I1 by I2 will be equal to N1 by N2. So which implies that N2 from here, N2 I can substitute it to be I2 by I1 into root 2 into N1. So N2 value I got. So this is my equation number. So this is my equation number 9. So substituting 9 in 8, I can write uh, I2 by I1 into root 2 into N1 into I1 into I2 from this thing equal to 36. So from this I2 square equal to I2 into I2 square equal to 36,000 into I1 into root 2 by N1. You have the value of I1, N1. I'm going to substitute it. So it comes out to be 36,000 into I1 is 20 into root 2 by N1 is 900. So I'm just cutting it up. So it is 40. So it comes out to be how much? Can someone quickly calculate this value? For me, it comes out to be 33.63. So this I2 square and I2 will be square root of this particular thing and it comes out to be. So I have got the value of I2. Now I can substitute it into I2. We have it to be 36,000 from equation number 8. So N2 will be nothing but 36,000 by 33.635 and it comes out to be how much? 107.0.236. So, is there any doubt in this question? I'm just substituting the values after finding out the relationships. So in this particular question, it was given that initially the series windings of the 8 poles are connected in series, that the series field winding was connected in series to get a single series resistance so that the field current is same as of that of the armature current. So a single current flows through all the circuit. Now the series windings are recombined in such a way that it forms two parallel paths such that a particular section of the field winding will carry half the current. So the new current will be I2 by 2. So this will form the new value of current. So that is the new condition. So now since the field windings are carrying half the current, so the flux will be proportional to the new armature current, the new current which is applied by the load by the uh, by 2, so it will be I2 by 2. So the I am just applying this basic equation, that is EB equal to K phi into N. So there I am substituting the different condition, that is the initial value of speed, initial value of the current. Since in the initial condition the field current as well as the armature current are same, so it will be I1 only. So and the load torque is nothing but Kt into phi into Ia. So the armature current and field current are same. So the load torque is proportional to the current square. So now we need to find the new speed and new current for this particular new combination of the field resistance. So I am taking the different values of that back EMF equation. I am simply using the same equation, that is K phi into Ia. And since the magnetizing curve is given to you as a linear thing, so we can assume we can take the condition that the flux is proportional to I. So the whatever the field current is passing through the field winding. So here the new field current is I by 2. So EP will be some proportional to I by 2 into N2, that is the new field current into N2. So and the torque will be proportional to the new field current into the total armature current. So it will be I2 square by 2. So, and also it was mentioned that the load torque is proportional to N square. So I am writing the relationship like this, that is TL1 by TL2 will be nothing but N1 by N2 the whole square. And at steady state we can see that the torque, the load torque is equal to the electromagnetic torque. So there I am applying the electromagnetic torque equation as well. So we will get a relationship between I1, I2 and N1 and N2, and that is our one main equation. And earlier we have written a equation connecting the back EMF and the field current and the as well as the speed. So if you take the ratio, the constant of proportionality will go. So and so EB1 by EB2 will be nothing but I1 N1 by I2 by N2. So I1 N1 by I2 by 2 into N2, because the current is now half. So we can write it as to be this particular expression, which is relating the back EMFs with the two currents as well as the two speeds. So in the question, we have not been provided any data regarding the resistances, that is the armature resistance as well as the effective field circuit resistance. So we can consider that the total series resistance, that is the total series resistance, to be negligible. So we can approximate the back EMF to be approximately equal to that of the voltage, the supply voltage. This is the important assumption we are taking. So then we can say EB1 by EB2 equal to 1. So this equation is reduces to an AC expression, that is EB1 by EB2 relation will be 1. So we will get a relationship between I1, I2 and N1 and N2. Just substituting this thing, we will get a relationship between I2 and N2. These are the two unknowns. And using the other equation of torque, you can get another equation connecting I2 and N2, which are the two unknowns, because here I1 is known, N1 is known. So you just substitute the values, and now after just it is a matter of substitution, you've got a relationship. So let me write it here it as I2 into initial speed was 900 and the initial current was 20 into root 2. So there was one more equation, which is I2 into N2 equal to 36,000. So from these two equations on solving, there is two unknowns and two equations. So I just substituted N2 here from the first equation and then solved for I2. So is there any doubt in this particular question?
No, sir.
I hope it's clear. So if you are not taking this assumption, then it will be very difficult. So if this assumption is taken, it is very clear. So then if there are no doubt, we can move to the next question. So this is also a DC series motor. So once you see a DC series motor, let me draw the equivalent circuit. So this is the field winding. So whenever you see a question regarding DC series motor, you should draw this circuit, and whenever you see a shunt motor, you should draw the shunt circuit. So you will get more or less an idea regarding the question, and remaining will be a basic circuit level question. So the main thing is to draw the circuit initially and to identify the different things given to you. And it is a 220 volt DC series motor. So V is given to you as 220 volt. And here in this question, they have been provided us with the armature resistance. So RA is given to you as 0.4 ohm. Let me read the question first, and then we can identify the things. A 220 volt DC series motor has an armature resistance of 0.4 ohm and a field resistance of 0.3 ohm. It is running at 600 RPM, so initially, while drawing 10 ampere current from the supply, and the load torque is given to be a constant. So here the load torque is constant, and the magnetizing curve is linear, and then a 0.7 ohm diverter is connected in parallel with the series field. it is given, and estimate the new field and the new motor. So let me. mm, so Ra is given to you as zero point 0.4 ohm, and the field resistance is given to you as zero point 0.3 ohm. So the initial field resistance is zero point 0.3 ohm is given to you. Now it is given that let me call it EB1. So this is case 1, and at this particular condition, so this is the actual circuit and we are not disturbing it at all. So at this particular condition, the motor is running at a speed of N1 is 600 rpm. So N1 is given to you as 600 rpm, and it is drawing a 10 ampere current. So this is the current. So there is no other path for the current. So the initial current I1, which is flowing through both the series winding as well as the armature terminal, is given to you as 10 ampere. So the current is also given to you and it is 10 ampere, and the load torque is constant. So TL equal to constant. So if you can see here that load torque is a constant. So the problem is more easier than the previous case where it was like TL. In the previous case, TL was proportional to n square. So these kind of loads we call a fan load, and this is a constant load. So in this problem, this is not the case, and it is given that the load torque is a constant. And again, it is given that the magnetizing curve is linear, so we don't need to worry about that. So phi is proportional to IF, so it is also given to you. So if you can see here, phi1 is proportional to I1, because here the field current as well as the armature current, that is the supply current, everything is same because there is no other path. So it is just a series connection. So the current through all the circuit parts will be the same, and it is I1. It is also given. And now it is this condition can be obtained from this particular statement, that is magnetizing curve is linear. And now let us go to the case 2. So let's identify what is given in case 2. Then it is mentioned that a zero point 0.7 ohm diverter is connected in parallel with the series field. Now this is the series field. So in parallel to the series field, so this is our circuit. I'm not disturbing this part. This part remains the same.
Sir, sir, I have a question arise for diverter. What is a diverter?
That's I'm coming to it, right? So diverter is nothing but we will add a resistance in parallel to the field circuit. So here what happens, we are adding a resistance, a variable resistance in parallel to the initial field winding. So this I am calling it as RSC, and this I am calling it as R diverter. And this diverter, what will it have? So there will be a current I2 coming, and that same current I2 will flow to the armature terminals RA and EB2. But here if you see, the current which is flowing through the field resistance will be IF2, and the current which is flowing through this path I am calling it as R diverter. Now, by introducing a resistance in parallel to the field resistance, the current through the field winding changes, because some part of the current will flow through the parallel resistance and only some part will flow through the field winding. So here by doing so, we are modifying the field current, so that we are actually here diverting the current away from the field circuit through introducing an extra path, right? So that's why we are calling it as a diverter, because we are diverting some part of the current through another parallel path. Still, do you have any confusion regarding what is a diverter?
Sir, the main work of the diverter resistance is reduced to total resistance of winding.
No, the to reduce the field current. So initial field current will be same as I1, right? Now the field current will be some portion of the net current which is being supplied. Some part of the current will flow through this part and some part of the field current will some current will only flow through the field winding. The other path will flow through some extra resistance.
Okay, sir. Okay, sir. I understand. Okay. Proceed further.
So in this condition, you can write the flux will be proportional to IF2, right? So phi2, in the first case, phi1 was proportional to the supply current I1, and in the second case, that is in case 2, now the flux phi2 is proportional to IF2, and now you can simply apply a voltage division, that is IF2 is nothing but R, the opposite resistance R div by R div plus RSC into I2. So I'm just applying voltage division, that is current division rule here. That is, the current through the field resistance will now be a fraction into the net current. So this is the catch. So this forms the entire thing which is forms the main crux of the problem. So first, it is given that initially a series motor was there and a current I1 which is equal to 10 ampere is flowing through the motor from the supply, and the armature resistance as given to you as 0.4 ohm and the field resistance was 0.3 ohm, and the voltage supplied is 220 volt. Now to the same system, we are introducing a diverter resistance in parallel to the same system. So RSC will remain the same as the previous case. RA will be the same, and EB2 will change because the current I2 can change. And so V will also remain the same, that is 220 volt. Now we need to find the value of new speed, that is the speed N2 and the new motor current. N2 equal to question mark and I2 equal to question mark. So these are the things we need to find. So is there any doubt in this so far? Is there any doubt so far?
Sir,
Yes.
sir, to find IF2, we are use
Yes.
current division rule.
What? Current division rule. Yes.
Okay, okay, okay.
Yeah. So because current, as per current division rule, the current through this path will be the opposite resistance by the sum of these two resistances into the current injected current. So that is just, you can apply the KCL rule and get this particular equation. This is the current division. So it's, let us write the basic equation, that is EB equal to K phi into N. So this is one basic equation, and torque equal to K phi into IA. So these are the two basic equations. So entire problem now revolves around this particular condition, and let me start it. So it is given to you that in the first condition, phi1 equal to k into some k phi into I1. So we can write EB equal to k into phi1, EB1 equal to k into phi into N1, and N1 is given to you. So you can write it to be, since it is linear, so I can write it as k dash into I1 into N1. So this forms our first equation. Similarly, TE1, which is at steady state, TE at steady state T equal to TL. So we can write TE1 equal to KT into phi into IA. And for this particular condition, you can write it as KT dash into I 1 square, because IA and IF are the same. So I'm writing our, in other words, it is KT dash into IF into IA. And for the first condition, you can see that IF and IA, they are same and it is equal to I1. So I can write it to be E1 to be KT dash into I1 square. So this is our second equation. And similarly, you can write EB2 to be K dash into IF2 into N1. This is our third equation. And TE2 equal to KT dash into IF into IF2 into IA2. So in the second condition, IA2 is I2, which I am taking. So TE2 will be nothing but KT dash into IF2 into I2. So this forms my fourth equation. So is there any doubt so far in writing this equation? I am just using the basic equation and I am giving suffixes 1 and 2 for the two cases. So is there any doubt so far? Is there any doubt in writing this equation? In substituting any of these values, any doubt?
Sir, I have two field current in the condition 2 and condition 2 current I2 just alike, right? Both are same.
No, because IF2 will be now this ratio into I2, right? So IF2 is the current which is only flowing through the field winding I am taking. So it is not equal to I2. It is different. That's why I have denoted it as a separate expression. In the first case, there was no diverter resistance. That way, I can use this expression, that is I1 square. But here, IF2 and I1 are different. And here also, it is N2. Sorry for the mistake here.
Okay, sir. Okay, sir. Okay.
So now I can simply, I have been given what is the value of field diverter resistance is given to you. So from the first equation, let me apply KVL and I can find out the value of EB1. So if I apply one more basic equation, so EB is V minus IAR. So in the first path, I can apply KVL. So EB1 will be nothing but V minus I1 into the total series resistance, right? So RA plus RC. This is for a series motor. RA plus RC will come in the net path. So it is I1 into RA plus RC. So it is same. So it is 220 minus I1 is 10 into zero point 0.4 plus zero point 0.3 and it is 213 volt. So this is 7. So it is 213 volt. So we got the value of EB1 and it is just a KVL equation. So these are the three basic equations for a series motor. The same equation, everywhere same equation. And if you know the circuit and how the circuit changes, then it is just the basic three equations. So if you have a hold of these three basic equations and how the value of IA, flux, and everything is related for a series motor as well as for a shunt motor, then the problem is quite easy. So we got the value of EB1. Now we need to find the value of IF2. So IF2 is nothing but the R diverter by the R diverter plus RC, right? So RC is given to us 0.3 and R diverter, that R DAV I am representing is 0.7. So it is 0.7 by zero point 0.7 plus zero point 0.3 into I2. So I2 is nothing but 0.7 times I2. So IF2, we got another relationship which is connecting IF2 and it is 5. So then just taking the ratio of the two EMFs, so I can get EB1 by EB2 is nothing but I1 N1 by IF2 N2. So this is the first expression. And next expression will be TE1 by TE2 equal to I1 square by IF2 into I2. So we have already got IF2 equal to I1 square, 0.7 into I2. So we can write, and it is given that the load torque is a constant, so it is equal to 1. So you get that 0.7 I2 square equal to I1 square. So I2 is nothing but I1 by 0.7. Good. So that will give you the value of I1. So is there any doubt so far? So I2 square will be nothing but this thing. So I2 will be nothing but 10 square by 0.7 I2 square. So it comes out to be 10 by root of 0.7 and it is 11.952 M. So, is there any doubt so far? I am just substituting the condition that I have the value of IF2. I am just substituting the value of two resistances. So I got a relationship which is connecting IF2 and the current I2. So, and it is given that the torque is a constant. So, as mentioned in the question, it is given that the load torque is constant. So, I am just using that condition. And I know the relationship between torque and the currents. So, T1 is some constant into I1 square, that is T1 proportional to the square of the armature current in the first case. And the second case, the torque is proportional to IF2 into IA2. So IA2 is nothing but I2 and IF2 is zero point 0.7 times I2. So I'm just substituting it here. So I got a relationship as I1 square by zero point 0.7 I2 square equal to 1. So I'm just cross multiplying it. So I got the value of I2. So I2 I got. Now we need to find the value of mm, uh, N2 is the thing which we need to find out. So we got the value of new motor current. So we need to find the value of N2. So for N2 we can write, we can see that EB1 by EB2 equal to I1 N1 by IF2 we have zero point 0.7 I2 and N2. So in this particular expression, if you see, you have the value of EB1, you have the value of I1, you have the value of N1, you have found out the value of I2. So there are two unknowns, that is EB2 and N2. But here, if you can see, you have already found out the value of I2. Now you can apply KCL in this particular branch because to find. So if you apply KCL in this particular branch, so let me draw that branch only, and there is a resistance here. So there is a current I2 which is injected, and there is a voltage V appearing, and there is a resistance, and there is a RA, and this current is also I2, and this current is now split into IF2 and I divider, and this is RSC, and this is RA, and this is the vacuum of EB2 for the circuit. So if you write KVL in this particular loop, in this bottom loop, so I can write it to be V equal to IF2 into RSC, that is V minus plus I2 into RA plus EB2. Just KVL in this particular loop. So if I am rearranging it, EB2 is nothing but V minus IF2 RC minus I2 into RA. So in this particular expression, if you see, we have the value of V, we have the value of IF2, we have the value of RC, we have the value of I2, we have the value of R. So everything is known to us. So we can just simply substitute it to be 220 minus IF2 we need to find out. IF2 is zero point 0.7 times I2. It is 0.7 into whatever we got, it is 11.952. 11.952 into RSC is 0.3, right? Yeah. So RSC is 0.3 minus I2 is 11.952 into RA is 0.4, 0.4, right? Yeah, 0.4. And substituting the values, you got the value of back EMF to be 212.70928. So I'm just here. If you can see, there is resistances value as given, so we cannot approximate the voltage to be approximately same as that of the back EMF because we have the value of resistances. So since this particular parallel combination is there, I am not going into that. So I am just applying KVL in the bottom loop because here also we can apply the KVL. So in this KVL loop, I can write that V minus IF2 into RC in minus I2 into RA minus EB2 will be equal to 0. So same equation I am using it here. I am just applying the KVL and finding out the value of EB2 which was unknown to us. Now we can substitute this EB2 in this particular first equation and then find out the value of N. So let me substitute it. So we have EB1 by EB2 is nothing but I1 N1 by 0.7 I2 into N2. So here you can write N2 to be nothing but EB2 by EB1 just cross multiplying into I1 by I2 into N1 by 0.7. So on substituting it, EB2 is nothing but 212.70928 by EP1 is 213 and I1 is 10, I2 is 11.952 and N1 is how much? N1 is 600 and 0.7. So on substituting, we go it should be 716.1755. Okay. So I'm just substituting the values here. We already have all these values available, readily available to us. I'm just substituting the values and just get the value of the speed. So in this particular problem, so it is given that initially a series motor was there and the value of the series resistance, that field resistance, the series field resistance, the armature resistance as well as the supply voltage is given to you. And this particular condition, what is the current drawn from the supply is also given to you. And it is given that the load torque is a constant. So this is one important consideration. And the magnetizing curve is linear. So you can assume the flux to be proportional to the current which is flowing through it. So I1 is proportional to I1. And now they are modifying the circuit such that they are adding a diverter resistance in parallel to the field winding so that the current through the field winding is now different and it is not equal to that of the and it is not equal to that of the current, the initial current, which is the same as that of the armature current. Now the current through the field winding, I am representing it as IF2. Now in order to find out the value of IF2, I am just using the current division rule, that is opposite resistance by the sum of the two parallel resistances. That is the current through this path is nothing but the opposite resistance by sum of these two resistance through the net current which is flowing through the network. So I am just applying the current division. Now they are asking us to find out the new value of speed and the new value of current I2 which is flowing through the motor in this particular condition. So I am using the three basic motor equation, that is that of the back EMF, the electromagnetic torque as well as the KVL equation which is relating the back EMF with the supply voltage and the armature current flowing through that. So we just apply the KVL in this particular loop without any diverter resistance. So I am just getting V minus I1 into RSC plus RA minus EB1. So from that I can get the value of EB1. Now I'm taking two conditions. That is the first condition without any diverter resistance. So I got the value of EB1 to be proportional to I1, that is the current through both the windings, both the armature as well as the field winding, into the speed, and the torque will be nothing but proportional to I square, because in that particular condition the current through the field winding as well as the armature winding are the same. So we got a relationship between torque and the currents. And in the second condition, it is the new field current IF2 into N2, which is EB2, and the torque is IF2 into the armature current, and the armature current I am calling it as I2. And now I have just substituted the value of the diverter resistance and the series field resistance value. So I got a relationship between IF2 and I2, and it is that IF2 is 0.7 times the supply current. So and now I am using, and it is given that the load torque is a constant. So I got a relationship between I1 and I2 as like this. So I can find out the value of I2 because I1 is already available to us. So I got the value of I2 to be 11.952 as against 10 ampere in the previous case. Now I can make use of the another expression which is available to us, that is the relationship between back EMF and the speed and the current. But here there are two unknowns, so we need to find one more variable. So for that I am making use of the KVL equation in the bottom loop, and so the KVL equation is applied, and I found out the value of the back EMF. After finding out the value of back EMF, I am substituting it in the expression to get the value of N2, as N2 is the only unknown here. So is there any doubt in this question? Is there any doubt in this question?
No, sir.
No, sir.
Okay. If there is there any doubt in any of the section which has covered? So if there is no doubt, we will wind up because it's already time. So thank you guys for listening to the session.
Thank you, sir.
Thank you.